Hello everyone and welcome back to the channel. In the vast landscape of distributed systems, nodes are constantly being added, removed, or failing. How do all these individual components know about each other's state or share crucial information without relying on a single central coordinator that could become a bottleneck or a single point of failure? The elegant solution is often gossip protocol. In system design interviews, demonstrating and understanding of gossip protocols shows a truly advanced grasp of decentralized consistency and fault tolerance. Today, we are diving into their fascinating world. So, let's try first to understand the problem that gossip protocol solves. The core problem gossip protocols address is decentralized information dissemination and membership management in large clusters. So think about that. We have a problem with centralized approach. You could have a central registry service where all nodes report their status, but this registry becomes a bottleneck of failure and a massive bottlenecks as the cluster scales. Also, we need to agree on something like need for agreements, like nodes need to agree on which nodes are currently active membership, the least configuration. Maybe they also need to agree on the state of shared data, like partition data assignments, things like that. So how do you get information also to propagate quickly and reliably across hundreds of thousands of nodes, even when some nodes are failing or network segments are unstable? Gossip protocol is the answer. So what is a gossip protocol? Gossip protocol, it's a decentralized peer-to-peer communication protocol where nodes periodically exchange information with small randomly chosen subset of other nodes in the system. Okay? Think of it how rumors or gossip spread within a social network. You don't tell everyone, you tell a few friends, and those friends tell a few friends of their friends, and so on and so forth. Information eventually diffuse throughout the entire group through these random pairwise interactions. So the core idea, it achieves eventual consistency of system states, meaning all nodes will eventually have the same information through this highly robust, decentralized, and probabilistic message exchange. Okay, so let's try to understand how it works. So we will have a cluster, we will have multiple nodes. In this cluster, okay. So the first thing would be it's the periodic exchange. Like each node in the cluster will periodically, like every 1 to 3 seconds, initiates a gossip round. This is a very frequent low overhead activity. So how does it work? We will have like random peers. Like in each round, the node randomly selects a small number of other nodes. It will be like 1 to 3. It will be very small constant number regardless of the cluster size. And yeah, so we have, for example, for this round, let's call it this N1 and N2, N3, 4, 5, and 6. So N1 will choose 2 nodes now, which will be N4 and N5. So again, we have a new round, and in each round, the node that initiates the round will choose 2 to 3 nodes. After that, we will have information exchange, like the communicating nodes then exchange the state information. It can be like push information, like the initiating node sends its local state, or maybe could be a pull initiation. Basically, the initiating node requests state information from the randomly chosen peer. And also we can use like a push pull, and I would say this is the most robust and most common. Basically, the initiating node sends its states and the peer nodes simultaneously sends its states back. This is highly efficient for coverages. Convergence, not cover. Convergence. Sorry. So right now, again, N1 will initiate a new round. It will send its status. It will choose two random peers, and after that, it will send its status to these peers, and the peers will send their status back. If you want to talk about the convergence, here the information about new nodes, failed nodes, or updated data eventually propagates throughout the entire cluster, even with a small number of peers per round. The information diffuses exponentially quick. If you want to think about some things like failure detection, nodes also include heartbeats or liveness information about themselves and other nodes they know about within their gossip message. If a new node constantly doesn't receive heartbeat from a peer, I guess for a predefined timeout, it eventually subsets that peer is dead and flags it as such to the rest of the cluster. So again, for example, let's just take a real world example here. So N1 will initiate a new round. It will try to connect with two random peers with N5 and N4. They exchange some information. For example, they will change information about the nodes that been connected to. For example, N4 have been connected to N2 and N3, and N2 doesn't respond back. So N4 will say, from my side, I connected with N3 and N4. N3 responded. N2 didn't respond. And N5 was connected also with, before this round, was connected with N6 and N2, and also N2 wasn't responding to it. So when they send requests to, when they exchange the information, they will say, okay, N5 and N4, they say that N3 and N6 are okay, but N2 has a problem. So also in the next round, let's take an example when N6 try to make a communication. So maybe it will send a random request to N1 and N3, for example. And for N1 has the information that N2 doesn't work. N3 maybe was connected with N5 and N4, and also they have information about N2 that doesn't work. So from a simple gossip protocol, which is randomly choosing peers, we got the information that N2 does not work, and all the nodes here are aware of each other and aware of their status. Okay. So why gossip protocol matters in system design? First, we have decentralization. They eliminate any single point of failure or bottleneck for state synchronization. Every node contributes to the information dissemination. Number two, high availability and fault tolerance. Information propagation is highly resilient, even if some nodes fail or network partitions occur temporarily. Information will eventually converge throughout the remaining active nodes. The system keeps functioning. Number three, massive scalability. They scale exponentially well to every large cluster. Basically, again, they scale exponentially well to every large clusters. Become the communication overhead per node is constant and doesn't depend on the total cluster size. Each node only talks to a few other nodes, and that's it. Next, we have eventual consistency. They inherently lead to eventual consistency of clusters' wide state, like membership lists or configuration values. I guess number 5, resilience to network partitions. Information might eventually reconverge correctly after network partition heal, without requiring manual intervention. Lastly, something about system design interview. I would say discussing gossip protocols demonstrates a sophisticated understanding of decentralized systems, membership services, and how to achieve constant state in a fault-tolerant manner. Okay, so let's talk about the challenges and considerations you would face in gossip with the gossip protocol. Number one, I would say which I guess it's a pretty obvious one, it's the eventual consistency. It's not suitable for strong immediate consistency needs. There is an inherent delay for information to propagate throughout the cluster. Number two, debugging. I would say it can be harder to trace why a specific piece of information isn't propagated or why node is misbehaving due to the probabilistic and decentralized nature. Number three, network overhead. They generate constant background network traffic, which needs to be considered for network bandwidth. Number four, convergence time. While usually fast, it can take measurable time for information to reach all nodes in a very large cluster, especially if the node is unstable. And lastly, we have false positive. A node might be subjected dead or announced as dead due to temporary network issue rather than an actual crash. Okay, no, yes. So how to discuss it in new systems design interviews? I would say in a systems design interview, bring up gossip protocols when discussing decentralized coordination, membership tracing, eventual consistency for shared state, or robust failure detection. Construct them with centralized approaches, explain the rumor spreading analogy, and mention key applications like Apache Cassandra, Console, or Redis cluster. It showcases announced understanding of distributed systems beyond just the basic. So yeah, that's it for this video, and see you in the future.